Question 1, and we're given a network with 8 vertices, and we are told to use Kruskal's algorithm to find a minimum spanning tree. So we must know which algorithm is Kruskal's. There is a little reminder in the question where it says you should list the arcs in the order in which you consider them. In each case, state whether you are adding the arc to your minimum spanning tree or whether you're rejecting it. So that's a little reminder that in Kruskal, we need to begin by listing the arcs in order of size, in ascending order. Now in an exam situation, you must do that as quickly as you can because it's only 3 marks, this part of the question. So to save time, I've already done that. It's all the arcs in order of size, and I've checked carefully that I haven't missed any. I haven't made any daft mistakes. So now we can get on with adding them to our tree, and each time saying whether we are or we are not adding it to our minimum spanning tree. Well, the first 2 edges will always be included in Kruskal, so I'm going to tick them both. And normally I would draw this out separately to check for cycles, but in this video I'm just going to highlight the edges as I add them to the tree. So the first edge in the tree is DE and the second one FG. Now notice those 2 edges are not connected. It's impossible to travel from example E to G on my current tree. There's a gap, it's not connected. And this happens sometimes with Kruskal's algorithm. You might have heard the phrase Kruskal is chaotic, and that's what we mean here. Edges could appear anywhere on the network, not even be connected. However, in Prim's algorithm, it's not chaotic. Every edge we add is connected to the tree, and it's always connected, it just grows. So the first 2 will always be accepted into the tree because there's no danger of having a cycle or a circuit after just 2 edges. That is when we would reject an edge if it gave us what we call a cycle or circuit. So now we're going to look at the third one, CD. Can we add that to our tree? Well, there's CD. Yep, that's fine. No circuit. So tick to say, yes, that's been added to the tree. Next up, we have BD. So BD, that's fine. So I can tick to say, yep, we can add that to our tree. Now you might notice BD and CE have the same weight of 24. So it doesn't matter which one of these I consider first. I could have considered CE first and then BD. But I went with BD first, and that's fine. The next one is CE. So there's C, there's E. However, if I added CE to my tree, then I have a cycle from C to D to E back to C. That's what we call a cycle or a circuit. So therefore, I'm going to reject CE. I could either write the word reject or just quicker to put across. So the next one, EG. There's E, there's G. That's fine. No circuit there, no cycle. I can add EG to our tree. Even though it connected 2 nodes that were already part of the tree, they were from different parts of the tree that were unconnected, and EG connected them. So there's no cycle there. EF next. EF, that's no good. We have a cycle there, so I'm going to reject EF. Now, when would I stop doing this algorithm? Well, I'd stop when all the vertices are included in the tree. At the moment, A and H are not included. So as soon as they get included, I will then stop the algorithm, and that will be the end of part A. So let's look up next. We have CF. CF, that's no good. We have a cycle here, CF, from C to D to E G, F, back to C. That's an example of a circuit or cycle. So we're going to reject CF. AC next, and then that connects A to our tree. Yep, so I can tick to say, yep, AC, which leaves us just H. There's only H we need to connect into the tree, which tells me that the next one, AB, that's no good. We get a cycle or circuit there. Remember, cycle and circuit mean the same thing. So reject AB. GH next. Now notice that's the first edge to involve H. Let's just check we don't get a circuit. So GH, yep, that's fine. Tick. And now that every single vertex is included in the tree, I don't even need to consider the last two. I can just say stop now that every vertex is in the tree. And that's all. We have full marks there for part A.